Even now, in what feels like perfect stillness, the body is traveling at 67,000 miles per hour around a star that itself drifts through the arm of a spiral galaxy, motion so constant, so ancient, that it has become indistinguishable from rest. There is something strangely comforting in this. The knowledge that stillness has never truly existed, that every moment of quiet has always been a kind of voyage, carried forward by forces older than the earth itself. The breath slows, the limbs grow heavy, and yet the journey continues through the dark, through the endless turning of worlds within worlds. If these quiet hours bring a sense of ease, perhaps leave a subscribe, a small way to return on other restless nights. The cosmos is patient, and so this telling can be patient too, unhurried, drifting, beginning now. As you lie there now, settled into the familiar weight of your own body against the mattress, you might notice how completely still everything feels. The sheets have grown warm against your skin, and the pillow has found its accommodation with the curve of your neck, and the whole room seems to rest in a kind of quiet equilibrium. Perhaps you can feel the gentle pressure of the blanket across your chest, rising and falling almost imperceptibly with each breath, and perhaps the sounds of the house have receded into that comfortable background hum that accompanies the late hours. There is nothing quite like this sensation, this feeling of being absolutely, thoroughly stationary, of having arrived at a place of rest where motion has ceased and the body can simply be. And yet, as we shall discover together over the course of this gentle exploration, this feeling of stillness is perhaps one of the most profound illusions that our senses have ever constructed for us. It is a beautiful illusion, a necessary one even, but an illusion nonetheless, and understanding its nature may bring you not distress, but rather a kind of quiet wonder at the remarkable circumstances of your existence. The ancient Greeks, whose careful observations of the natural world laid so many foundations for human thought, arrived at what seemed to them an obvious and self-evident truth about the nature of the cosmos. They looked up at the night sky and watched the stars wheel overhead in their stately procession, and they felt beneath their feet the solid, unmoving ground, and they concluded, quite reasonably by the standards of direct experience, that the earth must be the fixed and immovable center around which all other celestial bodies revolved. This idea, which we now call the geocentric model, was not born of foolishness or lack of intelligence, but rather from a deep trust in the evidence of the senses, a trust that you yourself might feel right now as you lie there in your apparently motionless bed. Aristotle, that great systematizer of ancient knowledge who lived some 23 centuries ago, articulated this view with particular clarity and persuasive force. For Aristotle, the earth occupied its rightful place at the center of the universe not merely by accident, but by its very nature. Heavy things, he reasoned, naturally moved toward the center, which was why stones fell downward and why the earth itself had gathered into a great sphere at the lowest point of all existence. The heavens above were composed of an entirely different substance, a perfect and eternal material called ether, and the celestial bodies moved in perfect circles because circular motion was the most perfect kind of motion, befitting their divine and unchanging nature. Below, in the realm of earth and water and air and fire, Things moved in straight lines toward their natural places, and once they arrived, they stopped. The Earth had arrived at its natural place, and so the Earth was still. This was not merely a philosophical position for Aristotle, but something he believed could be demonstrated through observation and careful reasoning. He proposed what later thinkers would call the Tower argument, a thought experiment that seemed to prove beyond doubt that the Earth could not possibly be in motion. Imagine, Aristotle suggested, that you stand at the base of a tall tower and drop a stone from its highest point. If the Earth were truly spinning beneath us, as some had occasionally speculated, then, during the time the stone took to fall, the ground below would have moved some distance to the east. The stone, no longer connected to the tower, would not share in this motion, and so it would land some distance to the west of the tower's base. But this is not what happens. When you drop a stone from a tower, it falls straight down, landing precisely at the base, exactly where you would expect it to land if the Earth were perfectly stationary. Therefore, Aristotle concluded, the Earth does not move. This argument, elegant in its simplicity, seemed utterly compelling. It matched the direct experience of every person who had ever lived, and it accorded with the deep intuition that we all carry within us. The intuition that says we would surely feel it if we were moving, that motion is something that announces itself to the body. For nearly 2,000 years, across the flowering and fading of civilizations, through the rise of Rome and its long decline, through the centuries we call medieval, and into the first stirrings of what would become modern science, this view persisted. It persisted not because people were incurious or because they refused to question, but because it explained the evidence of their senses so completely and so satisfyingly. The Earth was still. The heavens moved around us. And that was simply how things were. What those ancient thinkers could not have known, lying in their own beds on warm Mediterranean nights, feeling just as stationary as you feel now, was that the human body comes equipped with a sensory system that is exquisitely designed to detect certain kinds of motion while remaining completely blind to others. This system, which we now call the vestibular system, resides in the inner ear, tucked away in small chambers of bone that house some of the most delicate and sensitive structures in your entire body. There are tiny hair cells bathed in fluid, and there are small crystals of calcium carbonate called otoliths, which literally means ear stones. And there are 3 semicircular canals oriented in 3 different planes to detect rotation in any direction. This is the apparatus that tells you which way is up, that allows you to balance on one foot, that lets you know when you are nodding your head or tilting to one side. But here is the crucial detail that explains so much about our intuitions regarding motion and stillness. The vestibular system does not detect motion itself. It detects changes in motion. When you are sitting in an airplane that has reached its cruising altitude and settled into steady flight, your vestibular system reports nothing unusual, because there is nothing unusual to report as far as it is concerned. The fluid in your semicircular canals has settled. The otoliths have found their resting positions, and your brain receives signals indistinguishable from those it would receive if you were sitting motionless in a chair at home. It is only when the motion changes, when the plane accelerates or decelerates or turns or encounters turbulence, that your vestibular system springs into action and alerts you to movement. Constant velocity, no matter how fast, feels exactly like stillness. This limitation has been quantified by modern researchers, who have determined that the human vestibular system typically cannot detect linear acceleration below approximately 1/10 of a meter per second squared. Above this threshold, you will feel the push or pull of changing motion, but below it, your body's motion detectors remain silent, convinced that nothing worth reporting is occurring. And so a smoothly gliding elevator might fool you, and a train pulling gently away from a platform might leave you uncertain whether you are moving or the train beside you is moving. And the rotation of the Earth, which happens so gradually and so steadily, produces no sensation at all. It was Galileo Galilei, writing in the year 1632, who offered what remains perhaps the most beautiful illustration of this principle, though he framed it in somewhat different terms than we would use today. In his great work defending the Copernican view that the Earth moves around the Sun, Galileo asked his readers to imagine themselves below deck on a large ship, in the main cabin, with some friends and various objects for experimentation. Bring some small flying creatures, like butterflies, he suggested, and some fish in a bowl, and a bottle arranged to drip water slowly into a vessel beneath it, and observe how everything behaves when the ship is at rest. The butterflies will fly equally in all directions. The fish will swim without preference. The water drops will fall straight down into the receiving vessel. And if you toss something to your friend, you will need to throw it with equal force, regardless of the direction. Now, Galileo continued, have the ship move with whatever velocity you please, so long as the motion is uniform and not fluctuating this way and that. You will discover not the least change in any of the effects mentioned, and none of them will tell you whether the ship is moving or standing still. You will not need to throw an object with more force in one direction than another to cover the same distance. The water will continue to drip straight down into the vessel. The butterflies will continue their random flights without clustering at one end of the cabin, and the fish will swim about their bowl with perfect indifference. The motion of the ship, being shared equally by everything within it, simply vanishes from experience. What Galileo understood, and what Aristotle could not have known to consider, was that the stone dropped from the tower does not simply fall, it also continues moving with the tower, and with the earth to which the tower is attached. The stone carries its horizontal motion with it as it falls, and so it lands at the base of the tower, not because the earth is still, but because everything, stone and tower and earth and observer, is moving together. The tower argument, so compelling for 2 millennia, contained a hidden assumption, the assumption that motion would somehow make itself evident, that the stone would know it was supposed to stop moving horizontally simply because it was no longer in contact with the tower. But motion does not announce itself in this way. Motion, in the absence of forces to change it, simply continues, silently, invisibly, undetectably. And so we return to you, lying there in your bed, feeling so perfectly at rest. Your vestibular system is quiet, detecting no acceleration worth mentioning. The room around you shows no signs of motion. The walls are where they have always been. The ceiling remains overhead. And if you have a glass of water on the bedside table, Its surface is flat and still. Everything conspires to convince you that you have achieved true stillness, that you have come to rest in the most absolute sense of the word. But what if this conviction, so natural and so universal, is in fact an elaborate illusion, constructed by a sensory system that was never designed to detect the kinds of motion that actually characterize our situation in the cosmos? What if, at this very moment, even as your body reports nothing but stillness, you are being carried through space at velocities that strain the capacity of human language to describe the velocities, so great that the numbers seem almost abstract, almost meaningless, and yet represent your actual, physical, continuous motion through the universe? This is not a metaphor or a manner of speaking. It is not a philosophical puzzle or a trick of perspective. It is the simple, factual, measurable reality of your situation as you lie there feeling so wonderfully motionless. You are moving right now, and you have been moving since the moment you were born, and you will continue moving until the end of your days. And indeed, your body will continue moving long after you have ceased to be aware of anything at all. The speeds involved are not small. They are not gentle. They are, by any human standard, absolutely enormous. And yet here you lie, feeling nothing, suspecting nothing, wrapped in the comfortable illusion that your body and your senses have so carefully maintained. In the sections that follow, we shall trace these hidden motions one by one, beginning with the rotation of the Earth beneath you and moving outward through layer after layer of cosmic movement, each one carrying you along at its own particular velocity, all of them adding together in ways that are not always simple to calculate, until we arrive at a comprehensive picture of just how much motion is concealed within this apparent stillness. But for now, it is enough simply to rest with this gentle realization, to let it settle into your awareness like the warmth of the blankets settling around you, that the stillness you feel is real in its way, as real as any experience can be, and yet it is also an illusion, a beautiful and ancient illusion that the human body was never equipped to see through, until the long work of science slowly, patiently, revealed what had been hidden all along. Let us begin, then, with the first of these hidden motions, the one closest to your own body, the one carrying you in a great slow circle, even as you lie perfectly still in your bed, even as your breathing deepens and your thoughts begin to drift toward the edges of sleep. This is the rotation of the Earth itself, the gentle spin of our world around its own axis, a motion so constant and so smooth that you have never once felt it, not in all the years of your life, and yet it is carrying you now, at this very moment, in a vast arc through the darkness. To understand how we came to know about this motion, we must travel back through the centuries to a small cathedral town in northern Poland, a place called Frauenburg, which sits along the shores of a quiet lagoon that opens eventually to the Baltic Sea. The year was 1543, and in a modest house near the cathedral, an elderly man lay dying. His name was Nicolaus Copernicus, and he was 70 years old, and he had spent much of his life working quietly as a church administrator, a physician, an economist, and in whatever hours remained to him, an astronomer of extraordinary patience and vision. For decades, Copernicus had been developing a theory that contradicted nearly everything his contemporaries believed about the structure of the heavens. The accepted view, inherited from the ancient Greeks and refined by generations of scholars, held that the Earth sat motionless at the center of the universe, while the Sun, the Moon, the planets, and all the distant stars revolved around it in crystalline spheres. This seemed obvious enough if you simply looked up at the sky and watched the sun rise in the morning and set in the evening. Watched the stars wheel slowly overhead through the night. Surely we are still, people thought, and surely it is the heavens that move. But Copernicus had spent years making careful observations and performing laborious calculations, and he had come to believe something quite different. He proposed that the Earth was not the fixed center of creation, but rather a planet like the others, and that it moved in two ways simultaneously. First, it traveled in a great orbit around the Sun, completing one full circuit each year. And second, it spun on its own axis, completing one full rotation each day. This daily spin, he argued, was the true cause of the apparent motion of the Sun and stars across the sky. They were not circling around us at all. Rather, we were turning beneath them, like a child spinning slowly in a garden, while the trees and clouds seemed to wheel overhead. Copernicus had written all of this down in a book he called De Revolutionibus Orbium Celestium, which translates roughly as On the Revolutions of the Celestial Spheres. He had worked on this book for many years, refining his arguments, checking his mathematics, adding observations and diagrams. And yet he had hesitated to publish it, knowing how controversial its claims would be, knowing that many would consider it not merely wrong but dangerous, a challenge to scripture and tradition alike. It was only in the final years of his life that he was persuaded by friends and admirers to allow the book to be printed, and even then he delayed as long as he could, making corrections and revisions until the very end. The story is told, and it may be true, or it may be a gentle legend that has attached itself to history, that a copy of the finished book was brought to Copernicus on the very day of his death, the 24th of May, 1543. By then, he had suffered a stroke and was drifting in and out of consciousness, and it is said that he touched the pages of his life's work and then passed away, perhaps knowing that his ideas would outlive him, perhaps not knowing anything at all in those final moments. What is certain is that he never saw the controversy his book would eventually cause, never witnessed the slow and difficult process by which his heliocentric theory would come to be accepted, challenged, refined, and ultimately confirmed over the following centuries. What Copernicus proposed was correct in its essentials. The Earth does spin. It makes one complete rotation approximately every 23 hours, 56 minutes, and 4 seconds, a period we call a sidereal day, though we usually round this to 24 hours and make small adjustments to keep our clocks aligned with the position of the Sun. And because the Earth is a sphere, or very nearly so, this rotation means that different parts of its surface are moving at different speeds. If you were standing at the equator, that imaginary line that circles the Earth at its widest point, you would be moving toward the east at approximately 1,040 miles per hour. This is a remarkable speed, faster than the cruising velocity of most commercial aircraft, and yet you would feel nothing at all. No wind in your face, no sense of motion, no indication whatsoever that you were hurtling through space at such a pace. The air moves with you. The ground moves with you. Everything in your immediate environment shares the same velocity, and so the motion is imperceptible. But as you travel away from the equator, toward either the North Pole or the South Pole, the speed of your rotation gradually decreases. This is because you are tracing a smaller circle with each rotation. At the equator, you must travel the entire circumference of the Earth, roughly 25,000 miles, in the course of a single day. But at higher latitudes, the circle you trace is smaller, and so your speed is correspondingly reduced. At the latitude of Paris, for example, which lies about 49 degrees north of the equator, the rotational speed is only about 700 miles per hour. At the latitude of London, slightly to the north, it is similar. At the Arctic Circle, it is slower still. And if you were to travel all the way to one of the poles, to stand at the very top or very bottom of the world, something curious would happen. You would still complete one full rotation every 24 hours, just like everyone else on Earth. But you would be spinning in place, turning around and around on a single point, like a figure skater executing a slow rotation with arms extended. Your lateral speed, your movement through space in a sideways direction, would be reduced almost to nothing. You would be carried in a circle no wider than your own shoulders, pivoting gently beneath the stars that wheel directly overhead, completing the same rotation as the equator, but covering almost no distance at all. For more than 3 centuries after Copernicus published his theory, the rotation of the Earth remained something that had to be accepted on faith, or deduced from indirect evidence, or calculated from astronomical observations. No one had ever demonstrated it directly, in a way that ordinary people could see with their own eyes. The motion was too smooth, too constant, too perfectly shared by everything around us to be perceived without special instruments or careful reasoning. This changed in the winter of 1851, in Paris, when a self-taught physicist named Jean-Bernard Léon Foucault performed an experiment that would make the invisible rotation of the Earth visible for the first time. Foucault was a remarkable figure, the sort of person whose curiosity and technical skill compensated for any lack of formal credentials. He had begun his education studying medicine, hoping to become a surgeon, but he found that he could not bear the sight of blood, and so he abandoned that path and turned instead to physics. He never earned a university degree, never held an academic position in the traditional sense, and yet he made contributions to science that professors with long strings of letters after their names might envy. He improved the design of telescopes, developed new methods for measuring the speed of light, and invented a type of governor for regulating steam engines. But his most famous achievement was the pendulum that now bears his name. The idea behind Foucault's pendulum is deceptively simple. If you suspend a heavy weight from a long wire and set it swinging, it will continue to swing back and forth in the same plane, maintaining its direction through space even as the Earth rotates beneath it. The pendulum, in a sense, remembers its original direction, while everything else in the room slowly turns. And so, if you watch the pendulum carefully over the course of several hours, you will see its swing appear to rotate, tracing out a gradually changing path across the floor. But it is not the pendulum that is rotating. It is you, and the floor, and the building, and the entire earth beneath your feet. Foucault first demonstrated this principle privately, in the cellar of his house, using a pendulum with a wire only 2 meters long. The effect was subtle, difficult to observe, but it was there. Encouraged by this success, he arranged for a larger demonstration, first at the Paris Observatory, and then, most famously, at the Panthéon, that great domed building in the Latin Quarter that serves as a monument to the distinguished figures of French history. Beneath the soaring dome of the Panthéon, Foucault suspended a brass bob weighing 28 kilograms from a steel wire 67 meters long. The length of the wire was important, as a longer pendulum swings more slowly and steadily, making the effect easier to observe. He set the bob swinging in a careful, controlled manner, and then he invited the public to come and watch. What they saw astonished them. The pendulum swung back and forth in a long, graceful arc, and as the hours passed, its plane of oscillation appeared to rotate, slowly and steadily, in a clockwise direction. A stylus attached to the bottom of the bob traced lines in a bed of sand arranged on the floor beneath it, and these lines gradually shifted, showing the changing orientation of the swing at the latitude of Paris. The rotation proceeded at a rate of approximately 11 degrees per hour, which meant that over the course of a full day, the pendulum would appear to complete slightly more than one full circuit around the compass. The crowds who gathered to watch were witnessing something extraordinary, not because the pendulum was doing anything unusual, but because the earth beneath their feet was revealing its motion at last. Here was direct, visible, undeniable proof that the world was spinning, that Copernicus had been right all those centuries ago, that we are all of us passengers on a rotating sphere, whether we feel it or not. The rotation that Foucault made visible has consequences beyond the philosophical. Because the Earth spins, anything that moves across its surface over long distances must contend with a subtle but persistent deflection, a tendency to curve away from a straight path. This is called the Coriolis effect, named after the French mathematician Gaspard Gustave de Coriolis, who described it mathematically in 1835. The Coriolis effect arises because different parts of the Earth are moving at different speeds, as we discussed earlier. If you are standing at the equator and you fire a projectile due north, the projectile carries with it the eastward velocity of the equator. But as it travels north, it passes over land that is moving eastward more slowly, and so the projectile appears to curve to the right, toward the east. In the southern hemisphere, the effect is reversed, and moving objects appear to curve to the left. This deflection is far too small to notice in everyday life. If you throw a ball to a friend across a garden, the Coriolis effect will shift its path by a fraction of a millimeter, utterly insignificant compared to the effects of wind and spin and your own imperfect aim. But for large-scale motions, for things that travel great distances over many hours or days, the effect accumulates and becomes significant. Weather systems are the most dramatic example. When air flows toward a region of low pressure, the Coriolis effect deflects it sideways, causing it to spiral rather than move in a straight line. In the northern hemisphere, this deflection is to the right, And so cyclones and hurricanes rotate counterclockwise, spiraling inward toward their centers. In the southern hemisphere, the deflection is to the left, and so the great storms of that half of the world rotate clockwise. The vast pinwheel shapes of hurricanes, visible from space, are a direct consequence of the Earth's rotation, a reminder that even the weather is shaped by the spin of our world. And so here you are, lying quietly in the darkness, carried along by this first hidden motion. The room around you is turning. The building is turning. The city and the countryside and the oceans and continents are all turning together, completing one full rotation in the time it takes for a day and a night to pass. You cannot feel it. You will never feel it. And yet it is carrying you nonetheless, gently and ceaselessly, through the darkness. And so we come now to the second motion, which is rather larger than the first, and which carries you in a great sweeping arc around our local star, that familiar golden disk we call the Sun. This is the motion of Earth in its orbit, a journey that has continued without interruption for some 4.5 billion years, and which continues at this very moment as you settle into whatever comfortable position you have found for yourself. You are, at this instant, traveling at approximately 67,000 miles per hour relative to the Sun, which is to say 107,000 kilometers per hour if you prefer that system of measurement. And this speed is so great, and yet so smooth, that you cannot feel even the slightest whisper of it. There is no wind in your hair from this tremendous velocity, no sense of acceleration or deceleration, no vibration or rumble to suggest that you are hurtling through space faster than any vehicle humans have yet constructed for travel upon the Earth's surface. You are simply lying there, quite peacefully, while the planet beneath you sweeps through the void at a pace that would carry you from London to New York in approximately 3 minutes. Was such a journey possible in a straight line through space? This orbital velocity means that since this same time yesterday, since you last experienced whatever you experienced 24 hours ago, you have traveled roughly 1.6 million miles through space. Not relative to the ground beneath you, of course. For relative to the ground, you may have moved only a few miles in your daily activities, but relative to the Sun, that great furnace of hydrogen and helium around which we endlessly fall, you have covered a distance that would take a commercial aircraft flying continuously at cruising speed more than 120 days to complete. And you did not pack a bag, you did not book a ticket, you did not even notice it happening. You simply existed, and the Earth carried you along, as it carries everyone and everything upon its surface, in this perpetual circumnavigation of our star. Over the course of a full year, this journey accumulates to approximately 584 million miles, which is the total length of Earth's orbital path. If you were to stretch that path out into a straight line, it would reach from here to the Sun more than 6 times over, and yet we traverse it so regularly, so predictably, that we measure our very lives by its completion. Each birthday marks another full circuit, another 584 million miles added to your personal odometer, though of course nobody keeps such records except perhaps in whimsical moments of astronomical reflection, such as this one. By the time you reach the age of 80, should you be fortunate enough to do so, you will have traveled some 46 billion miles around the Sun, all while going about the ordinary business of human existence, eating breakfast and reading books and sleeping in beds much like the one you may be resting in now. The understanding of this orbital motion, the precise mathematical description of how planets move around the Sun, came to us through the work of Johannes Kepler, a German mathematician and astronomer who labored over the problem during the years between 1609 and 1619 while working in the city of Prague. Kepler was a man of unusual persistence and unusual patience, qualities that served him well in the tedious business of calculating planetary positions from observational data he had inherited, if that is the right word, a magnificent treasure of astronomical observations from his predecessor and sometime employer, the Danish astronomer Tycho Brahe, who had spent decades of his life meticulously recording the positions of the planets from his observatory called Uraniborg, which was built upon the island of Ven in the waters between Denmark and Sweden. Tycho's observations were the most accurate that had ever been made without the aid of a telescope, for the telescope had not yet been applied to astronomical purposes during most of his working life, and his records of the planet Mars were particularly detailed, comprising hundreds upon hundreds of careful measurements of where that rusty wanderer appeared against the background of fixed stars. Kepler took these observations of Mars, these painstaking records of its nightly position over many years, and he attempted to fit them to various mathematical models of planetary motion. The prevailing assumption of the time, inherited from the ancient Greeks and refined through the medieval period, was that planets moved in perfect circles, or in combinations of perfect circles, because the circle was considered the most perfect of geometric forms and therefore the most suitable for heavenly bodies. But the observations would not fit, no matter how Kepler adjusted his circular orbits, no matter how he added smaller circles upon larger circles in the manner of his predecessors. He could not make the mathematics match Tycho's careful measurements. And so, after years of calculation, after filling page upon page with numbers and geometric constructions, Kepler made a remarkable decision. He abandoned the circle. What Kepler discovered, through his persistent analysis of Tycho's Mars data, was that planets do not move in circles at all, but rather in ellipses, which are gently elongated circles, stretched along one axis like a circle that has been carefully pulled at two opposite points. This was his first law of planetary motion, that planets orbit the Sun in elliptical paths, with the Sun located at one of the two focal points of the ellipse rather than at the center. His second law described how planets move faster when they are closer to the Sun and slower when they are farther away, sweeping out equal areas in equal times as they progress along their orbital paths. And his third law, published in 1619, established a precise mathematical relationship between the size of a planet's orbit and the time it takes to complete one full circuit, allowing astronomers to calculate orbital periods from orbital distances and vice versa. These three laws, derived from Tycho's observations and Kepler's mathematical ingenuity, remain valid to this day, and they describe the very motion that is carrying you through space at this moment. Because Earth's orbit is an ellipse rather than a perfect circle, the distance between our planet and the Sun varies slightly throughout the year. In early January, around the 3rd or 4th of that month, Earth reaches its closest approach to the Sun, a point called perihelion, at which time we are approximately 91.4 million miles from the solar surface. In early July, around the 4th of that month as well, Earth reaches its most distant point, called aphelion, at which time we are approximately 94.5 million miles from the Sun. This difference of about 3 million miles, or roughly 3% of the average distance, is enough to cause a small variation in the intensity of sunlight reaching Earth, though this variation is far too slight to be responsible for our seasons, which are caused by the tilt of Earth's axis rather than by changes in our distance from the Sun. Indeed, those of us in the Northern Hemisphere experience winter when Earth is actually closest to the Sun, a fact that sometimes surprises people who have not considered the geometry of axial tilt. The reality of this orbital motion, the fact that Earth truly does move around the Sun rather than the Sun moving around a stationary Earth, was demonstrated through direct observational evidence in 1727 by an English astronomer named James Bradley. Bradley was working at Kew, near London, and he was attempting to measure something called stellar parallax, which is the tiny apparent shift in a star's position that should occur as Earth moves from one side of its orbit to the other, much as a nearby object appears to shift against a distant background when you view it first with one eye and then with the other. Parallax had been predicted as a consequence of Earth's motion around the Sun, but no one had yet managed to detect it because the stars are so tremendously far away that their parallax shifts are extraordinarily small, far smaller than the instruments of Bradley's time could reliably measure. What Bradley noticed, however, was a different kind of stellar shift, one that followed a different pattern than parallax would follow. He observed that stars appeared to be displaced slightly in the direction of Earth's orbital motion, and that this displacement changed systematically throughout the year as Earth's direction of travel changed. This effect, which Bradley called stellar aberration, is caused by the combination of Earth's velocity through space and the finite speed of light traveling from the stars to our eyes. Just as raindrops, falling vertically on a still day, appear to slant towards you when you walk quickly through them, so too does starlight, arriving from the depths of space, appear to slant slightly in the direction of Earth's motion. The faster Earth moves, the greater this apparent slant, and by measuring the angle of aberration, Bradley was able to calculate the speed of Earth's orbital motion. His result was remarkably accurate, agreeing with the modern accepted value to within approximately 1%, a testament to both his careful observations and his sound reasoning. This aberration of starlight provided direct physical evidence that Earth is in motion around the Sun, evidence that did not depend upon theoretical arguments or mathematical models, but rather upon the straightforward observation of stellar positions throughout the year. It was a gentle vindication of the heliocentric model proposed by Copernicus nearly 2 centuries earlier, and it demonstrated that the ancient intuition of a stationary Earth, however compelling it might feel to our everyday senses, does not correspond to the actual state of affairs in our solar system. We are moving, always moving, carried along in this great elliptical path by the gravitational bond between our planet and its star, and so you rest there now, participating in this second motion without effort or intention, completing your share of the 584 million miles that Earth will travel this year. The velocity is constant enough, smooth enough, that your body cannot distinguish it from perfect stillness. Your inner ear, that delicate apparatus of fluid and hair cells that alerts you to changes in motion, finds nothing to report. For there are no changes to report, only the steady continuation of a journey that began long before you were born and will continue long after you have departed. The tea in your cup, if you happen to have one, does not slosh towards one side due to orbital motion, and the flame of a candle, if you happen to have lit one, does not bend in any direction because of your tremendous velocity around the sun. This is the second motion, then a motion 60 times faster than the first, carrying you in a year-long loop around a star that has itself been burning for nearly 5 billion years. The Keplerian ellipse traces itself out beneath you, obeying laws that were deduced from observations made on a Danish island by a man with a golden nose, refined by a mathematician in Prague who refused to accept imperfect predictions, and confirmed by an Englishman at Kew who noticed that the stars themselves seemed to lean ever so slightly in the direction Earth was traveling. The calculations have been done, the observations have been made, and the motion continues, regardless of whether anyone is paying attention to it. You have moved, since you began listening to this section, some thousands of miles further along Earth's orbital path, and you will move thousands more before sleep finally arrives to quiet your conscious awareness of such matters. The journey requires nothing of you, asks nothing of you, and offers only the gentle reassurance that you are part of something far larger than the small patch of ground you happen to occupy at this moment, something that has been going on for billions of years and will continue for billions more. And so we come now to the third motion, a journey of such immense scale that it makes our planet's yearly orbit around the Sun seem like nothing more than a small circle drawn on a very large map. For just as the Earth carries us around our star, the Sun itself is not standing still. Our star, this great glowing sphere that warms our days and lights our mornings, is itself a traveler, moving through the vast reaches of our galaxy at speeds that would seem almost incomprehensible if we were to dwell upon them for too long, which we shall not. For tonight, we are simply letting these facts wash over us like gentle waves upon a quiet shore. The Sun, you see, is hurtling through the Milky Way galaxy at approximately 514,000 miles per hour, which translates to roughly 828,000 kilometers per hour for those who prefer metric measurements. And either way, it is a speed so great that no earthly vehicle could ever hope to match it. We do not feel this motion, of course, just as we do not feel the spinning of the Earth or our orbit around the Sun. And this is something of a comfort, really, to know that we can be carried along at such tremendous velocities while remaining perfectly at ease in our beds, our bodies unaware of the cosmic journey we are undertaking at this very moment. This motion carries us in a particular direction, toward a region of the sky that astronomers have identified with some precision over the centuries. We are moving toward the constellation Hercules, that ancient pattern of stars named for the hero of Greek mythology. And more specifically, we are heading toward what is called the solar apex, a point in the sky that lies not far from the bright star Vega. If you were to go outside on a clear summer evening in the northern hemisphere and look up at the brilliant blue-white light of Vega, one of the brightest stars in our sky, you would be looking very nearly in the direction that our entire solar system is traveling, carrying you and everyone you have ever known toward that distant region of space at more than 500,000 miles per hour. The discovery that our sun is moving through space was made by a remarkable astronomer named William Herschel, the same gentleman who discovered the planet Uranus and who spent much of his life mapping the heavens with telescopes he built with his own hands. In the year 1783, Herschel published a paper in which he analyzed the tiny apparent motions of just 13 stars, those subtle shifts in position that astronomers call proper motions. And from this small sample of data, he was able to deduce that our sun must be moving through space, carrying all its planets along with it. It is rather extraordinary to think that from observing the movements of only 13 points of light in the night sky, Herschel was able to determine a fundamental truth about our place in the cosmos, and his methods, though refined considerably since his time, remain the foundation upon which our understanding of solar motion is built. Herschel noticed that some stars appeared to be moving apart from each other over time, while others seemed to be converging, much like how trees on either side of a road appear to spread apart ahead of you and come together behind you as you walk along a country lane. By analyzing these patterns of stellar motion, he reasoned that the sun must be traveling in a particular direction, causing the stars ahead of us to appear to drift apart and those behind us to seem to converge. It was a beautiful piece of deductive reasoning, the kind of quiet intellectual triumph that does not make for dramatic storytelling, but which nonetheless changed forever our understanding of our cosmic situation. Now, this motion of the sun is not random wandering, but rather a great orbital journey around the center of our galaxy. The Milky Way, that faint band of light that stretches across the night sky in places far from city lights, is actually the combined glow of hundreds of billions of stars, all orbiting around a common center. And our sun is one of those countless stars, making its own slow circuit around the galactic core. This orbit is not a perfect circle, but something closer to an ellipse, and it takes an almost unimaginably long time to complete, somewhere between 225 million and 250 million years, a period that astronomers sometimes call a galactic year or a cosmic year, depending on their preference. 225 million years is so long that it becomes difficult for the human mind to truly grasp, and so perhaps it helps to think of it in terms of what was happening on Earth the last time our solar system occupied this particular position in its galactic orbit. The last time we were here, approximately 225 million years ago. The age of dinosaurs was just beginning to dawn. The great supercontinent of Pangaea was still largely intact, though it would soon begin to break apart, and the first small dinosaurs were emerging, creatures that would eventually give rise to the magnificent giants that would dominate the Earth for over 160 million years. All of that history, all of those millions of years of evolution and extinction and change, represents just one orbit of our sun around the galaxy, just one galactic year in the long life of our star. Since its formation approximately 4.6 billion years ago, our sun has completed only about 20 of these grand orbits around the galactic center. 20 journeys around the Milky Way is all the time there has been for our star to form from a cloud of gas and dust, to ignite its nuclear fires, to gather around itself a family of planets, and to nurture on at least one of those planets the conditions necessary for life to emerge and eventually to produce beings capable of contemplating their own cosmic journey. In galactic terms, our Sun is still rather young, with perhaps another 5 billion years of steady burning ahead of it before it exhausts its hydrogen fuel and begins the slow transformation into a red giant star. But that is a story for another time. And for now, we are concerned only with the motion, the gentle, ceaseless motion that carries us through the galaxy. The Sun's path around the galactic center is not perfectly flat, like a marble rolling around the inside of a smooth bowl, but rather involves a gentle bobbing motion, an oscillation above and below the main plane of the galaxy. The Milky Way, you see, is shaped rather like a fried egg when viewed from the side, with a central bulge surrounded by a thin disk of stars, gas, and dust. And our Sun weaves its way through this disk, rising above it and then sinking below it in a slow, undulating rhythm. This bobbing motion takes approximately 30 to 35 million years to complete one full cycle, carrying us perhaps 100 light-years above the galactic plane at the highest point of our oscillation before we drift back down through the plane and continue to the same distance below it. Some scientists have speculated that this bobbing motion might have consequences for life on Earth, as passing through the denser regions of the galactic plane could potentially expose our solar system to higher levels of cosmic radiation or increase the likelihood of gravitational disturbances from nearby stars. But these ideas remain speculative, and for our purposes tonight, we need only appreciate the gentle rhythm of this motion, the slow rise and fall that adds another layer of complexity to our cosmic journey. We are not merely circling the galaxy, but also gently waving up and down as we go, like a carousel horse that bobs while it circles, though on a timescale so vast that millions of generations come and go between each peak and trough of our galactic oscillation. At present, our solar system is located approximately 26,000 light-years from the center of the Milky Way galaxy, placing us roughly halfway between the galactic core and the outer edges of the stellar disk. This is sometimes called the galactic habitable zone, a region neither too close to the dangerous radiation and gravitational chaos near the galactic center, nor too far out in the sparse outer reaches where the heavy elements necessary for rocky planets and complex chemistry are less abundant. It is a comfortable middle distance, a suburban location in cosmic terms, and it has provided a relatively stable environment for our solar system over the billions of years of its existence. When astronomers study the motions of stars in our galaxy, they often find it useful to establish a reference frame called the local standard of rest. This is a conceptual tool, a way of averaging out the random motions of stars in our neighborhood to create a kind of baseline against which individual stellar motions can be measured. The local standard of rest moves in a circular orbit around the galactic center, and by comparing the motion of any particular star to this standard, astronomers can determine how that star's orbit differs from the average. Our Sun, as it happens, is moving at approximately 12 miles per second relative to the local standard of rest, a relatively modest peculiar velocity that suggests our star formed in this general region of the galaxy and has not been dramatically perturbed by close encounters with other stars or massive objects. The concept of the local standard of rest is a bit like establishing sea level as a reference point for measuring altitude. A useful fiction that allows for meaningful comparisons, even though the sea itself is not truly level and varies in height from place to place and moment to moment. Similarly, the local standard of rest is not a fixed point in space, but rather a mathematical construct that helps astronomers make sense of the complex dance of stellar motions in our galactic neighborhood. It is one of many such conceptual tools that astronomers have developed over the centuries to help them understand the cosmos. And while it may seem abstract and technical, it serves the very practical purpose of allowing us to describe where we are and where we are going in the vast reaches of the Milky Way. And so here we are, carried along by our star on its 225 million-year journey around the galaxy, bobbing gently above and below the galactic plane, moving toward the constellation Hercules at more than 500,000 miles per hour, and yet feeling none of it. We lie in our beds, in our quiet rooms, perhaps listening to the sound of the wind outside or the gentle creaking of our homes settling in the night. And all the while we are participating in a cosmic voyage of such grandeur that it defies easy comprehension. The dinosaurs did not know they were making this journey, and the creatures that will inhabit the Earth 200 million years hence will likely be equally unaware of it. And yet the journey continues regardless, patient and eternal, asking nothing of its passengers but their presence. This motion, this third layer of movement that we are adding to our growing understanding of our cosmic situation, is larger by far than the motions we considered before, the spinning of the Earth and the orbiting of our planet around the Sun. And yet, it is still not the largest motion we shall contemplate before our journey of understanding is complete. For just as the Earth orbits the Sun and the Sun orbits the galactic center, so too does our galaxy participate in even grander motions, drifting and falling through the cosmos in ways that we shall explore in the sections that follow. But for now, let us rest with this third motion, this grand voyage of our star, and let the numbers and the concepts settle gently into our minds like leaves falling slowly to the forest floor, not demanding to be fully grasped, but simply asking to be present, to be part of our dreaming thoughts as we drift ever deeper into the quiet peace of the evening, carried along by our star toward Hercules, toward Vega, toward wherever it is that the cosmos has determined we shall go. And so we arrive at a fourth motion, one that carries not merely you, not merely the Earth, nor even the Sun alone, but the entire Milky Way galaxy itself, drifting through the cosmos like a great luminous vessel upon an ocean without shores. This motion is so immense in scale that to speak of it in human terms requires a kind of gentle surrender to numbers that have long since departed from everyday meaning. And yet, these numbers describe something real, something happening right now, something that has been happening since before the Earth existed, and will continue long after the last traces of human civilization have returned to stardust. The galaxy that contains everything you have ever known, every person who has ever lived, every story ever told beneath the stars, is itself moving toward another galaxy, and it has been doing so for billions of years with the patient inevitability of gravity doing what gravity does best. The Milky Way is approaching the Andromeda Galaxy at approximately 250,000 miles per hour, which is to say roughly 400,000 kilometers per hour for those who prefer that notation. This is a speed that sounds rather alarming when stated so plainly. And yet, there is nothing alarming about it at all, because at such vast distances, even tremendous velocities become gentle, become almost imperceptible, become the kind of motion that unfolds across timescales so long that no human lifetime could ever witness any meaningful change. The collision between these two great spiral galaxies is expected to occur in approximately 4.5 billion years, give or take a few 100 million years, which is about the same amount of time that has passed since the Earth itself formed from the primordial disk of gas and dust surrounding our young sun. In other words, the approach has been happening for as long as planets have existed in our solar system, and it will continue for just as long again before anything particularly eventful occurs. To understand how we came to know this, we must travel back in time to the early decades of the 20th century, to a period when the very nature of the universe was still profoundly uncertain. When astronomers debated whether the fuzzy patches of light they observed through their telescopes were nearby clouds of gas within our own galaxy or something far more extraordinary. Among these fuzzy patches was one known as the Andromeda Nebula, visible to the naked eye on clear, dark nights as a faint smudge in the constellation that bears its name. And this particular object had puzzled astronomers for centuries without revealing its true nature. In 1912, an astronomer named Vesto Melvin Slipher was working at the Lowell Observatory in Flagstaff, Arizona, using a spectrograph to analyze the light from various nebulae. Slipher was a meticulous observer, patient and careful in his work, and he had developed techniques for capturing the spectra of these dim objects that required exposure times of many hours across multiple nights. When he turned his attention to the Andromeda Nebula, he discovered something rather unexpected in the way its light had shifted toward the blue end of the spectrum. This blue shift indicated that whatever the Andromeda Nebula was, it was moving toward us at a considerable velocity, approaching rather than receding, swimming against what would later be recognized as the general cosmic tide of expansion. Slipher had measured one of the first galactic blue shifts ever recorded, though at the time he could not have known the full significance of what he had found, because the question of whether Andromeda was a galaxy at all remained unanswered for another decade. The resolution came in 1923, when an astronomer named Edwin Hubble was working at the Mount Wilson Observatory in the mountains above Los Angeles, using what was then the largest telescope in the world, the 100-inch Hooker telescope, named for the businessman who had funded its construction, gathered light through a mirror more than 2.5 meters across. And with this instrument, Hubble was able to resolve individual stars within the Andromeda Nebula for the first time. Among these stars, he identified a type of variable star called a Cepheid, which pulses in brightness with a period that is directly related to its intrinsic luminosity. By measuring the period of this Cepheid's pulsation, Hubble could determine how bright it truly was, and by comparing this to how bright it appeared, he could calculate its distance. The result was startling. The Andromeda Nebula was not a cloud of gas within our Milky Way at all, but rather a separate galaxy entirely, lying at a distance of approximately 900,000 light-years, which was far beyond the boundaries of our own stellar system. Later measurements would revise this distance upward to approximately 2.5 million light-years. But the essential point remained unchanged. The universe had suddenly become incomprehensibly larger, filled with island universes scattered across gulfs of emptiness that the human mind could barely begin to contemplate. With Hubble's discovery, Slipher's earlier observation of the blue shift took on new meaning. Here was another galaxy, comparable in size and grandeur to our own Milky Way, and it was approaching us. The two great spirals were moving toward each other through the void, drawn together by the invisible threads of gravitational attraction, beginning a dance that would unfold across billions of years. This knowledge might seem rather dramatic when first encountered, the idea of two galaxies on a collision course. And yet, like so many things in astronomy, the drama dissolves upon closer examination into something far more serene. The Milky Way and Andromeda are both members of what astronomers call the Local Group, a modest congregation of galaxies bound together by mutual gravitational attraction within a region spanning approximately 10 million light-years. This is the neighborhood in which our galaxy resides, if one can speak of neighborhoods at such scales, and it contains more than 80 known galaxies of various sizes and types. Most of these are small, dim dwarf galaxies, barely visible even to powerful telescopes, scattered around the two dominant spirals like attendants around twin monarchs. The Triangulum Galaxy, also known as Messier 33, is the third largest member of the Local Group, a respectable spiral in its own right, though considerably smaller than either the Milky Way or Andromeda. There are also numerous dwarf spheroidal galaxies, dwarf irregular galaxies, and other diminutive stellar systems, some containing only a few million stars, others somewhat larger but still modest by galactic standards. Within this local group, all the member galaxies are in motion relative to one another, orbiting around their common center of mass, which astronomers call the barycenter. The Milky Way itself moves relative to this local group barycenter at a velocity of several hundred kilometers per second, tracing out a path through space that is influenced by the gravitational pulls of Andromeda and all the smaller galaxies besides. This motion adds yet another component to the grand cosmic journey you are undertaking as you rest quietly in bed. Another layer of velocity stacking upon all the others we have discussed. Another current carrying you onward through the universe while you remain perfectly still. In recent years, our understanding of local group dynamics has been refined considerably by data from the Gaia Space Observatory, a European Space Agency mission launched in 2013 to map the positions and motions of stars with unprecedented precision. By tracking the tiny apparent movements of stars across the sky, Gaia has allowed astronomers to measure the three-dimensional velocities of not only stars within our own galaxy, but also the proper motions of nearby galaxies themselves. This precise choreography of local group dynamics, revealed through painstaking observation and careful analysis, shows us that Andromeda is not approaching the Milky Way directly head-on, but rather at a slight angle, with a sideways component to its motion that will influence the eventual nature of the merger. The Gaia data suggests that the collision may be somewhat less direct than earlier estimates indicated. with the galaxies possibly executing a glancing encounter before eventually settling into a single combined system over billions of years. But here is the part that may gently reassure you as you drift toward sleep. When we speak of galaxies colliding, the word collision conjures images of catastrophic destruction, of stars smashing into one another in brilliant fireballs of released energy, of worlds torn apart and scattered across the void. And yet, this is not at all what happens when galaxies merge, because galaxies are almost entirely empty space. The distances between individual stars within a galaxy are so vast, and the stars themselves are so tiny in comparison, that two galaxies can pass through one another with scarcely any direct stellar collisions at all. It is rather like two swarms of gnats flying through each other on a summer evening, the individual insects passing harmlessly between one another despite the apparent density of the swarms, because there is so much empty air between them. Consider that the nearest star to our Sun is Proxima Centauri, lying at a distance of approximately 4¼ light years. If we were to scale the Sun down to the size of a grain of sand, roughly 1 millimeter across, then Proxima Centauri would be another grain of sand, located approximately 6 kilometers away. A galaxy, on this scale, would be a collection of perhaps 200 billion grains of sand, scattered across a region tens of thousands of kilometers in extent, with similar distances of many kilometers between each neighboring grain. When two such collections merge, the grains drift past one another without touching, influenced only by the gentle gravitational stirring that reshapes their orbits over millions of years. Stars that once followed orderly paths through the disk of a spiral galaxy find themselves flung onto new trajectories. Some cast outward into extended halos, others drawn inward toward the merged galactic center, but almost none actually striking another star directly. The likelihood of our own Sun experiencing a direct collision with another star during the Andromeda merger is so small as to be essentially negligible. The gravitational interactions will certainly alter stellar orbits, and the shape of the resulting merged galaxy will be quite different from either of its progenitors, likely forming a large elliptical galaxy rather than maintaining the graceful spiral structure of the Milky Way or Andromeda. But the individual stars, including our Sun, if it still exists at that distant time, will continue on their journeys largely unharmed by the encounter. The merger will unfold over hundreds of millions of years, a slow gravitational minuet rather than a violent collision, and any beings who might exist to witness it would see a gradual transformation of the night sky rather than sudden destruction. Not that any humans are likely to witness this event from Earth, of course. In 4.5 billion years, the Sun will have exhausted the hydrogen fuel in its core and begun its transformation into a red giant star, expanding outward to engulf the inner planets and rendering Earth uninhabitable long before the galactic merger reaches its climax. But this is simply the way of things in a universe governed by patient physical processes, where stars are born and die, where galaxies drift and merge, where everything changes gradually across timescales that dwarf the entire history of life on our small world. For now, in this present moment, as you rest in the quiet darkness of your room, the Milky Way continues its unhurried approach toward Andromeda, adding yet another velocity to your cosmic journey. The motion is imperceptible. As all these motions are imperceptible to our limited senses, and yet it is real and measurable and continuing right now, carrying you along with everything else you have ever known toward an eventual merger that lies as far in the future as the formation of Earth lies in the past. There is something rather peaceful in knowing this, in understanding that you are part of a galaxy in motion, part of a local group in gravitational embrace, part of a universe that is vast beyond comprehension and yet still governed by comprehensible laws. And as you continue to rest, perfectly still in every way that matters to your immediate experience, another motion carries you onward, another current flows through the cosmic ocean, another journey unfolds across billions of years while you sleep. There is a kind of motion that asks nothing of you, that requires no awareness and no participation, and yet it carries you along just the same, as surely as a leaf is carried by a river whose current it cannot see and whose destination it cannot know. This is the fifth motion we shall consider together, and it is perhaps the strangest of all, because it speaks of forces that pull upon you from distances so vast that the light describing them has traveled for hundreds of millions of years before reaching the instruments we have built to detect it. You are being drawn, at this very moment, towards something enormous and largely invisible, something that astronomers discovered almost by accident and still do not fully understand. And this gentle gravitational summons has been acting upon you since long before the Earth existed, since long before the Sun condensed from its cloud of primordial gas, since the very architecture of the cosmos began to take its present shape. The story of how we came to know about this invisible pull begins in the middle of the 1980s, when a small group of astronomers set out to measure something that had troubled their colleagues for years. They wanted to understand why the cosmic microwave background radiation, that faint afterglow of the universe's earliest moments, appeared slightly warmer in one direction of the sky and slightly cooler in the opposite direction. This asymmetry, called a dipole, suggested that our entire galaxy was moving through space at considerable speed, creating a kind of Doppler shift in the ancient light, washing over us from all directions. But the question remained as to what could possibly be pulling us along. What gravitational source could be massive enough to influence the motion of an entire galaxy and all its hundreds of billions of stars? The team that took up this question consisted of 7 astronomers whose work would prove so significant and whose collaboration was so productive that they came to be known informally as the 7 Samurai, a name borrowed from a classic film about warriors who band together to accomplish what none could manage alone. Among them were Alan Dressler, who had spent years studying how galaxies cluster together in space; Sandra Faber, whose contributions to understanding galaxy formation would earn her numerous honors throughout her career; and Donald Lyndon Bell, a British theoretical astrophysicist known for his work on the dynamics of stellar systems. Together with their colleagues David Burstein, Roger Davies, Gary Wegner, and Roberto Terlevich, they embarked on a systematic survey of elliptical galaxies, measuring their distances and velocities with unprecedented precision, looking for patterns in the way these vast stellar cities moved through the cosmos. What they found, when they published their results in 1986, was that the motion of our galaxy could not be explained by the gravitational influence of the nearby Virgo cluster alone. Even though Virgo contains over 1,000 galaxies and sits relatively close to us in cosmic terms, instead, there appeared to be something else, something much more massive and much farther away, lying in a direction where their instruments could barely see. The team proposed that an enormous concentration of matter, perhaps equivalent to tens of thousands of galaxies, was pulling not just our Milky Way, but the entire local group of galaxies, and indeed the Virgo cluster itself, toward a common destination at a speed of approximately 370 miles per second. They called this unseen mass concentration the Great Attractor, a name that captures both its function and its mystery. For it is great in the sense of being incomprehensibly massive, and it attracts in the sense that its gravity reaches across hundreds of millions of light years to nudge everything in our cosmic neighborhood toward itself. The region of sky where the Great Attractor seemed to reside presented an immediate and frustrating problem for astronomers hoping to study it directly. It lay in the direction of the constellations Centaurus and Hydra, in a band of sky that passes through the thickest part of our own galaxy's disk. When you look toward the center of the Milky Way, you are peering through vast clouds of interstellar dust and gas, through billions of foreground stars whose light overwhelms the faint glow of distant galaxies, through a region so opaque to visible light that astronomers have given it a rather evocative name. They call it the zone of avoidance, because galaxy surveys have traditionally avoided it, knowing that the obscuring material of our own galaxy makes it nearly impossible to see what lies beyond. The Great Attractor, it seemed, was hiding in precisely the region of the cosmos where we were least able to look. This cosmic coincidence, this placement of a massive gravitational anomaly behind a curtain of galactic dust, might seem almost deliberately frustrating, as though the universe had chosen to conceal one of its most intriguing features in the one place we could not easily examine. But the universe, of course, makes no such choices, and the obstruction is simply a consequence of our position within a flattened spiral galaxy whose disk blocks our view in certain directions. The zone of avoidance wraps around the entire sky along the plane of the Milky Way, a band roughly 10 to 20 degrees wide, depending on how strictly one defines it. And within this band, the dust is so thick that optical telescopes can see almost nothing of the extragalactic universe beyond. Fortunately, not all forms of light are equally affected by interstellar dust. While visible light and the shorter wavelengths of the electromagnetic spectrum are scattered and absorbed by dust particles, longer wavelengths, such as infrared light and radio waves, can pass through more freely, and at the very short wavelengths of X-ray radiation, dust presents almost no obstacle at all. In the early 1990s, astronomers began turning these alternative forms of observation toward the zone of avoidance, hoping to glimpse what lay hidden behind the Milky Way's obscuring veil. And what they found confirmed that the Great Attractor region did indeed contain an enormous concentration of galaxies. X-ray observations proved particularly illuminating, revealing the presence of a massive galaxy cluster almost directly behind the densest part of the zone of avoidance. This cluster, now known as the Norma cluster or Abell 36-27, lies approximately 200 million light-years from Earth and contains hundreds of galaxies bound together by their mutual gravity. At the heart of the cluster sits an unusually active galaxy that emits copious amounts of X-ray radiation, betraying its presence even through the intervening dust. The discovery of the Norma cluster provided strong evidence that the Great Attractor was not merely a theoretical construct, but a real physical structure, or rather, a region of enhanced gravitational influence caused by an unusual concentration of matter in that part of the cosmos. And yet, the story did not end there. Because, as astronomers continued to map the motions of galaxies throughout our cosmic neighborhood, they began to realize that the Great Attractor was itself part of a much larger structure, and that the gravitational landscape of the nearby universe was more complex than anyone had initially supposed. The flow of galaxies toward the Great Attractor was real enough, but it appeared to be just one component of a more extensive pattern of cosmic motion. A grand streaming flow that encompassed hundreds of thousands of galaxies spanning hundreds of millions of light years. The tools for understanding these vast structures improved dramatically in the early years of the 21st century, and in 2014, a pair of astronomers named Brent Tully and Hélène Courtois, along with their collaborators, published a remarkable study that redrew our understanding of our place in the cosmic web. They had developed new techniques for mapping not just the positions of galaxies, but the flows of motion that connected them, tracing the gravitational basins that pulled groups of galaxies toward common centers. And what they found was a structure of truly staggering proportions. They discovered that our Milky Way, along with the local group and the Virgo cluster and the Great Attractor region, and tens of thousands of other galaxies, all belonged to a single enormous supercluster, a basin of gravitational attraction measuring approximately 520 million light-years across and containing perhaps 100,000 galaxies of various sizes. They named this supercluster Laniakea, a word that means immense heaven in Hawaiian, and the name seems fitting for a structure so vast that light itself requires more than 500 million years to cross it. Within Laniakea, all the galaxies are flowing generally inward, pulled toward the center of the basin by the combined gravity of everything the supercluster contains. Our local group sits near the outer edge of Laniakea, falling slowly toward its heart, participating in a motion that will continue for billions of years into the future. Though the ultimate fate of this journey remains uncertain, given the competing influence of the universe's accelerating expansion. The discovery of Laniakea was not simply a matter of naming a new structure on a cosmic map. It represented a new way of thinking about how the universe is organized, how gravity shapes the distribution of matter on the largest scales, and how motion itself can be used to define the boundaries between one supercluster and another. Just as a watershed on Earth can be defined by asking where raindrops would flow if they landed at any given point, Laniakea was defined by asking where galaxies would flow if they followed the local gravitational currents. The boundary of the supercluster is not a wall or a membrane, but simply the locus of points where the gravitational pull toward Laniakea's center gives way to the pull toward some other center, some neighboring supercluster with its own basin of attraction. And this brings us to another layer of the mystery, because even as Tully and Courtois were mapping Laniakea, other astronomers were pointing out that the motion of our supercluster itself seemed to be influenced by something even larger and more distant. Beyond the Great Attractor, in roughly the same direction but considerably farther away, lies an even more massive concentration of galaxies known as the Shapley supercluster. This enormous structure, named after the American astronomer Harlow Shapley, who first catalogued the unusual density of galaxies in that region of the sky, contains approximately 24 rich galaxy clusters and represents one of the most massive concentrations of matter in the observable universe within 1 billion light-years of Earth. Some astronomers have suggested that the Shapley supercluster may be the true dominant attractor in our region of the cosmos, that what we call the Great Attractor is merely a way station on a much longer gravitational journey, a local concentration of mass that participates in an even grander flow toward Shapley. The debate continues. Because the relative contributions of different mass concentrations to our overall motion are difficult to disentangle, and the measurements required to settle the question definitively are at the very edge of what our current instruments can achieve. What remains clear is that the gravitational landscape of the universe is lumpy and uneven, that matter has concentrated into structures ranging from galaxies to clusters to superclusters, and that these concentrations pull upon one another across distances that defy ordinary comprehension. So here you are, lying quite still in the quiet of this moment. And yet you are being pulled, very gently but very persistently, towards something you cannot see and will never reach. The Great Attractor and the Shapley supercluster and all the other mass concentrations in our cosmic neighborhood exert their influence upon you, accelerating you by tiny amounts that accumulate over billions of years into motions of hundreds of miles per second. You cannot feel this pull any more than you can feel the Earth's orbit around the Sun, because you and everything around you are all accelerating together, falling through space as one, like objects in a freely falling elevator that experience no sensation of weight. The zone of avoidance keeps much of this hidden from direct view, but we know it is there because we can see its effects, because we can measure the motions of galaxies and trace them back to their gravitational causes, because the universe reveals its secrets to patient observation even when it seems determined to conceal them. And there is something oddly comforting in the knowledge that we are being gathered up, that we belong to something larger than ourselves, that our little galaxy with its one small sun and its one small planet is participating in a cosmic journey that began long before we existed and will continue long after we are gone. The name Laniakea reminds us that the people who study these things are also poets in their way, reaching for words that capture the wonder of what they have found, choosing a Hawaiian phrase to describe an immense heaven that spans hundreds of millions of light years and contains more galaxies than any human could count in a lifetime. You are part of that immense heaven. You are made of the same matter that drifts in those distant galaxy clusters. You are moving through space with the same grand cosmic flow. And you may rest now in the knowledge that the universe has gathered you up and is carrying you along to wherever it is that everything is going. And so we come now to the deepest motion of all, the most fundamental measurement of our journey through the cosmos, one that connects us not merely to other galaxies or clusters of galaxies, but to the very origins of the universe itself, to light that has been traveling for almost 14 billion years before arriving at our instruments, at our eyes, at this moment in time. This is a motion measured not against stars or galaxies, which are themselves moving in their own complex dances, but against something far more ancient and far more universal. a kind of cosmic backdrop that permeates all of space and has done so since the universe was young enough to still be glowing with its first light. To understand this deepest motion, we must first speak of a discovery made quite by accident in the year 1965, at a place called Bell Telephone Laboratories in Holmdel, New Jersey, in the United States, where two radio astronomers named Arno Penzias and Robert Wilson were working with a rather unusual piece of equipment. This equipment was a large horn antenna, shaped somewhat like an enormous ear trumpet or a giant metal funnel lying on its side. And it had been built originally not for exploring the mysteries of the cosmos, but for the rather more practical purpose of detecting radio signals bounced off balloon satellites as part of early communication experiments. The antenna was exquisitely sensitive, designed to pick up the faintest whispers of radio waves from space, and Penzias and Wilson had been given the task of calibrating it for astronomical observations, which required them to identify and eliminate all sources of unwanted noise that might interfere with the delicate measurements they hoped to make. As they worked through the summer and autumn of 1964 and into the following year, they encountered a persistent problem, a faint but stubborn hiss of radio static that they simply could not explain away or eliminate no matter what they tried. The noise was always there, coming from every direction in the sky equally, unchanging whether they pointed the antenna north or south, east or west, whether they observed during the day or during the night, whether the Earth was on one side of its orbit around the Sun or the other. They checked their equipment meticulously. They accounted for radio interference from New York City, some 50 kilometers away. They even climbed inside the antenna to remove what they delicately referred to as a white dielectric material that had been deposited there by pigeons nesting in the horn. But still, the mysterious hiss remained, as constant and as inexplicable as before. A gentle whisper coming from everywhere and nowhere at once. What Penzias and Wilson had stumbled upon, quite without realizing it at first, was something that theoretical physicists had predicted might exist, but that no one had yet deliberately searched for: the faint afterglow of the Big Bang itself, the remnant radiation left over from a time when the entire universe was a hot, dense, glowing fog of particles and light. This radiation is called the cosmic microwave background, or CMB for short, and it represents the oldest light in the universe, light that was released approximately 380,000 years after the Big Bang, when the cosmos had cooled enough for atoms to form and for space to become transparent for the first time. Before that moment, the universe was so hot and so dense that light could not travel freely. It was constantly being absorbed and re-emitted by the sea of charged particles that filled all of space. But once atoms formed and captured those free electrons, the light was suddenly free to stream outward in all directions. And it has been traveling ever since, cooling and stretching as the universe expanded, until it now reaches us as a faint glow of microwave radiation coming from every point in the sky, the most ancient light we can ever hope to observe. This cosmic microwave background radiation is, in a very real sense, a photograph of the infant universe, an image captured when the cosmos was less than 400,000 years old. And it provides us with something remarkable and philosophically profound, a kind of absolute reference frame against which we can measure our motion through space. You see, Unlike stars or galaxies, which are scattered unevenly through the universe and are all moving in their own particular ways, the CMB radiation fills all of space uniformly, or very nearly so, and it is not moving anywhere because it is simply everywhere. The residual heat of creation itself, suffusing the entire cosmos like a very faint, very cold glow. If you were completely at rest with respect to the CMB, you would measure exactly the same temperature in every direction, about 2.7 degrees above absolute zero, and that temperature would be perfectly uniform no matter where you looked, a smooth and featureless backdrop of ancient light. But here is the thing, and this is what makes the CMB so useful for understanding our motion through the cosmos. We are not at rest with respect to this primordial light. We are moving through it, and because we are moving, we see a slight Doppler shift in the radiation, exactly like the Doppler shift that makes a passing ambulance siren sound higher in pitch as it approaches and lower as it recedes, or that makes light from approaching galaxies appear slightly bluer and light from receding galaxies appear slightly redder. When we move toward a source of light or radiation, the waves get compressed slightly, shifted toward higher energies and higher temperatures. And when we move away, the waves get stretched, shifted toward lower energies and cooler temperatures. And because we are moving through the CMB in a particular direction, the radiation appears very slightly warmer in the direction we are traveling toward and very slightly cooler in the direction we are traveling away from, creating what scientists call a dipole anisotropy, a gentle variation in temperature from one side of the sky to the other, with a warm pole ahead of us and a cool pole behind us, like the bow and stern of a great ship moving through a sea of ancient light. This dipole anisotropy in the cosmic microwave background radiation tells us something quite remarkable. It tells us the speed and direction of our absolute motion through the universe, our velocity relative to the oldest light there is. And when we make careful measurements of this temperature difference from one side of the sky to the other, we find that we are moving at approximately 627 kilometers per second, which works out to something like 1.4 million miles per hour, or 2.3 million kilometers per hour, in the general direction of the constellation Leo. This is a truly enormous velocity, far greater than any speed we have discussed so far, greater than the Earth's orbit around the Sun, greater than the Sun's orbit around the galaxy, greater even than our galaxy's motion toward the Great Attractor. And it represents the sum total of all our nested motions, plus something extra, what physicists call our peculiar velocity. The additional motion that arises from all the complex gravitational interactions between our galaxy, our local group, our supercluster, and the large-scale structure of the cosmos. The precise measurement of this cosmic velocity required instruments far more sensitive than the horn antenna at Bell Labs, and the definitive measurement came in 1992 from a satellite called COBE, which stands for Cosmic Background Explorer, launched by NASA in 1989 under the scientific leadership of a physicist named George Smoot. The COBE satellite was designed specifically to map the cosmic microwave background radiation with unprecedented precision, to measure not only the dipole anisotropy that reveals our motion through the cosmos, but also the much fainter fluctuations, The tiny ripples in the temperature of the CMB that represent the seeds of all the galaxies and clusters and superclusters that would eventually form as the universe evolved. Smoot and his team, along with a colleague named John Mather, who led another instrument on the satellite, were able to measure the CMB dipole with exquisite accuracy, confirming our velocity of roughly 627 kilometers per second toward Leo, and their work was recognized in 2006 with the Nobel Prize in Physics, a fitting honor for a discovery that connected humanity to the most ancient light in existence. In 2009, the European Space Agency launched an even more sophisticated satellite called Planck, which spent several years mapping the cosmic microwave background with even greater precision than COBE had achieved. And in 2013, the Planck team released their results, refining our measurements of the CMB dipole and providing the most accurate picture yet of our motion through the primordial light of the universe. These measurements confirmed and refined what COBE had found, placing our cosmic velocity at 627 kilometers per second, plus or minus just a few kilometers per second. A measurement of remarkable precision for a velocity so vast, and the direction was confirmed to be toward a point in the sky near the constellation Leo, between Leo and the neighboring constellation of Crater, where the cupbearer pours wine for the gods in ancient mythology. There is something philosophically profound about this measurement, something that invites quiet contemplation as you lie here in the stillness of your bed. The light that reveals our cosmic speed to us has been traveling for almost 14 billion years, since the universe was a young and glowing infant. And in all that time, it has been stretching and cooling as the cosmos expanded, fading from brilliant orange light to invisible microwaves, becoming ever fainter and ever colder with each passing aeon. And yet, it still carries within it the information about our motion, still reveals through its gentle Doppler shift the direction and speed of our journey through the universe. A journey we have been making without knowing it, without feeling it, for as long as humanity has existed and for billions of years before that. The ancient light remembers, in a sense, even when we do not, and it offers us the closest thing to an absolute measurement of motion that the laws of physics allow. You see, in the everyday world, we are accustomed to thinking of motion as relative, and indeed, Einstein's theory of relativity tells us that there is no such thing as absolute rest or absolute motion, that we can only ever speak of motion relative to some other object or reference frame. If you are sitting in a train moving smoothly along a straight track, you might feel as though you are at rest while the countryside moves past you. And in a very real sense, you would be right, because within the reference frame of the train, you are indeed stationary. But the cosmic microwave background provides something unique, a reference frame that is not tied to any particular object or location, but that fills all of space uniformly. The remnant glow of the entire universe at a specific moment in cosmic history, and our motion relative to this universal backdrop is as close to absolute motion as physics permits us to define. This does not mean that some cosmic authority has decreed that one velocity is correct and all others are wrong. The mathematics of relativity still holds, and motion is still fundamentally relative. But it does mean that there is a special reference frame, a preferred vantage point, if you will, defined by the light that has been traveling since the dawn of time, and we can measure our velocity relative to that vantage point with remarkable precision. We are moving at 627 kilometers per second relative to the ancient glow of creation. And that is a fact as solid and as measurable as the distance from here to the nearest star. And so, as you lie here, feeling perhaps very still and very quiet, you are in fact being carried through the cosmos at this tremendous speed, hurtling toward the constellation Leo at 1.4 million miles per hour, moving through a sea of ancient light that has been traveling since before the Earth existed, since before the Sun existed, since before our galaxy had finished forming from the primordial clouds of hydrogen and helium that emerged from the Big Bang. The light that reveals this motion to us is the oldest light there is, the first light that was ever free to travel through space, and it has been journeying toward us for almost the entire history of the universe, only to arrive at our instruments and whisper to us, through the gentle warming of one side of the sky and the gentle cooling of the other, the secret of our cosmic velocity. This is the deepest motion, the most fundamental journey, the one that connects us not merely to our solar system or our galaxy or our supercluster, but to the very fabric of the cosmos itself, to the light that was released when the universe first became transparent, to the glow that has been fading and cooling for 14 billion years, but that still remembers, still carries within it the information that allows us to know how fast and in what direction we are traveling through the ancient sea of creation. And so we come now to gather together all of these motions, to hold them gently in our minds as a single continuous journey, and to recognize that you, resting there so peacefully, are in fact a traveler of extraordinary velocity, carried along on currents of motion that nest one within another like the layers of some infinitely patient cosmic machinery, each orbit and rotation adding its own contribution to your passage through the universe, until the total speed of your journey becomes almost too large to hold in the imagination, and yet remains utterly imperceptible to your senses, as quiet and as gentle as the breath moving in and out of your lungs at this very moment. Let us begin once more with the Earth's rotation, that slow and faithful turning that carries you eastward through the darkness or the light, depending on where you happen to be resting, and which, at the equator, moves at roughly 1,040 miles per hour, though somewhat less at higher latitudes, where the circles of rotation grow smaller. And this motion alone would be remarkable if you could feel it, this constant eastward drift that brings the sun into view each morning and carries it away each evening. And yet your body notices nothing of this 1,000-mile-per-hour journey, because everything around you moves in precisely the same way. The air and the trees and the buildings and the birds all carried along together in one great rotating embrace. But this rotation is only the first and smallest of the motions we have explored together. For the Earth itself is falling continuously around the Sun, tracing out its great elliptical path through the void at a speed of approximately 67,000 miles per hour, which is to say about 18.5 miles every single second. A velocity that would carry you from one side of a modest city to the other in the time it takes to draw a single breath. And this orbital motion is itself nested within the rotation, so that you are simultaneously spinning and orbiting, turning on the surface of a world that is itself turning around a star. Two motions woven together into a single continuous path that spirals through space like the pattern left by a point on a rolling wheel. And this orbital speed is considerable indeed, faster by far than any vehicle that humans have yet constructed for travel within our atmosphere. And yet still, it represents only a fraction of the total velocity of your cosmic journey. For the Sun itself is moving, carrying the Earth and all the other planets along with it as it traces its own vast orbit around the center of the Milky Way galaxy. A journey that takes approximately 230 million years to complete and proceeds at the remarkable speed of roughly 514,000 miles per hour, nearly 500,000 miles in a single hour, a velocity so great that in the time since you began listening to this gentle exploration of motion, you have traveled thousands upon thousands of miles through the galaxy, carried along by the Sun as it falls endlessly around that distant and invisible center where millions of stars crowd together in ancient light. Now we must add still more to this accumulating velocity. For the Milky Way galaxy itself is not stationary, but moves through the local group of galaxies, drawn by gravity toward its eventual merger with Andromeda. And this motion contributes perhaps another 100,000 miles per hour to your journey, or somewhat more, depending on how one measures the relative velocities of these vast island universes. And beyond this local motion, there is the motion of the entire local group as it falls toward the Virgo cluster and the Great Attractor. Those massive concentrations of matter that pull gently but persistently on everything in their vicinity, adding yet more speed to the already substantial total. And finally, if we measure our motion against the most fundamental reference frame available to physics, the cosmic microwave background radiation that fills all of space with the afterglow of the universe's earliest moments, we find that the Earth and its Sun and its galaxy and its local cluster of galaxies are all moving together at a combined velocity of approximately 1.3 million miles per hour, which is to say about 370 kilometers every second. A speed so vast that the mind can barely grasp it, and yet so smooth and so unchanging that you feel nothing whatsoever of this tremendous journey, your body resting there in perfect peace while hurtling through the cosmos at a velocity that would carry you to the moon in just over half an hour, 1.3 million miles per hour. Then, is roughly the total speed of your passage through the universe at this moment. Though of course, this figure depends entirely on what we choose as our reference point. And this brings us to one of the most profound and beautiful insights of modern physics. The understanding first articulated clearly by Albert Einstein in his remarkable year of 1905. When he published his special theory of relativity and changed forever our understanding of space and time and motion, Einstein understood what Galileo had glimpsed centuries before, that motion is always and only relative, that there is no way to measure absolute velocity through space because space itself provides no fixed grid against which such measurements could be made. No cosmic milestone that remains truly stationary while everything else moves past it. And this means that the question of how fast you are moving has no single correct answer, but rather an infinite number of equally valid answers depending on what you choose as your reference frame. And all of these answers are true simultaneously, none more fundamental than any other. From the reference frame of the room in which you rest, you are perfectly still, and this is true. From the reference frame of the Sun, You are moving at 67,000 miles per hour around your annual orbit. And this, too, is true. From the reference frame of the galactic center, you are moving at over 500,000 miles per hour. And this also is true. And from the reference frame of the cosmic microwave background, you are traveling at 1.3 million miles per hour through the ancient light of the early universe. And this is equally and entirely true, all at once, without contradiction, because motion itself is not an absolute property of objects, but only a relationship between objects, a way of describing how the distance between things changes over time. This was Einstein's great insight, worked out in his miraculous year when he was just 26 years old, working as a patent clerk in Bern and thinking about what it would be like to ride alongside a beam of light. And from these peaceful contemplations emerged a revolution in physics that would reshape our understanding of the universe itself, revealing that space and time are not the fixed and absolute stage on which events unfold, but are themselves part of the performance, bending and stretching and interweaving in ways that depend on relative motion and the presence of mass and energy. And so, the ancient philosophical question that humans have pondered for thousands of years, the question of whether we are truly moving or truly still, turns out to have no absolute answer, not because the question is poorly formed or because we lack sufficient knowledge, but because the universe itself does not contain an absolute answer to give, because motion is always relative and never absolute, and stillness is simply motion measured against something that happens to be moving along with you. And this understanding, far from being unsettling, can be received as a kind of liberation, a recognition that your experience of peaceful rest is just as real and just as valid as the calculation of your cosmic velocity. Both perspectives true, both perspectives partial, both woven together in the beautiful and subtle fabric of relativistic space-time. Let us pause now to consider another journey, one even more remarkable than your current passage through the cosmos. And this is the journey taken by the atoms that compose your body, those carbon and oxygen and nitrogen and hydrogen atoms that have assembled themselves so elegantly into the form, resting there so peacefully. For these atoms have stories that extend back billions of years and across distances that dwarf even our current calculations of cosmic motion. The hydrogen atoms in your body, those simplest of atoms consisting of a single proton and a single electron, are among the oldest objects in existence, formed in the first few minutes after the Big Bang, when the universe was still a hot and dense plasma of elementary particles just beginning to cool enough for atomic nuclei to survive. And these hydrogen atoms have existed ever since, roughly 13.8 billion years, drifting through the cosmos, gathering into clouds, collapsing into stars, being expelled in stellar winds, and eventually finding their way into the cloud of gas and dust that collapsed to form our solar system some 4.5 billion years ago. And the heavier atoms in your body, the carbon that forms the backbone of your organic molecules, the oxygen that fills your blood with the capacity to metabolize energy, the nitrogen that builds your proteins and your DNA, the calcium in your bones and the iron in your blood. All of these were manufactured in the cores of ancient stars, forged in nuclear furnaces that burned for millions of years and then scattered their enriched material across space in supernova explosions or gentle stellar winds And these atoms then drifted for millions or billions of years more before being gathered up into new stars and new planets, and eventually into you. This is the meaning of the famous observation made by Carl Sagan in his television series Cosmos, first broadcast in 1980, when he spoke of how the nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, were all made in the interiors of collapsing stars, and how we are, in the most literal and precise sense, made of star stuff. And this phrase has echoed down through the decades because it captures something true and something beautiful about our place in the cosmic story. The recognition that we are not observers of the universe, but participants in it, made from the same material and subject to the same forces as the most distant galaxies and the most ancient light. The atoms in your body have traveled billions of light years over the course of their existence, carried along by the expansion of the universe itself and by their own wanderings through interstellar space. From the primordial fireball of the Big Bang to the cores of ancient stars to the nebulae where new solar systems form. And now they rest for a time in the beautiful and improbable pattern that is you, before eventually returning to the cosmic cycle, perhaps to be incorporated into some future star or some future world or some future form of life that we cannot begin to imagine. And this too is a kind of motion, a journey measured not in miles per hour, but in billions of years. A slow and patient voyage through the long reaches of cosmic time. And now let us consider where you are in this moment, resting there so peacefully, perhaps with your eyes closed or your mind beginning to drift toward sleep. And let us calculate how far you have traveled since we began this gentle exploration of motion. For if we take 1.3 million miles per hour as a reasonable estimate of your total cosmic velocity, and assume that perhaps 15 or 20 minutes have passed since we first began to speak of these things, then in that time you have traveled roughly 300,000 miles or more through the universe, a distance greater than the span from the Earth to the Moon, accomplished in perfect stillness, without the slightest sensation of motion, without any effort or awareness on your part whatsoever. You are, in this sense, a peaceful voyager on an eternal journey, carried gently through the cosmos by the accumulated motions of planetary rotation and orbital mechanics and galactic dynamics and the great bulk flows of matter responding to gravity across millions of light years, and yet appearing perfectly still, at rest on your bed or in your chair, breathing slowly, perhaps already beginning to feel the soft approach of sleep. And there is something deeply peaceful in this understanding, something that can serve as the ultimate lullaby of physics. The recognition that motion and stillness are not opposites, but partners. That rest is just as real when measured at 1.3 million miles per hour as it is when measured against the pillow beneath your head. The universe carries you along without asking your permission and without requiring your participation, just as it carries the planets around their stars and the stars around their galaxies and the galaxies through the vast cosmic web. And you are part of this great flow, this endless patient motion, this journey that began before you were born and will continue long after the atoms that currently compose you have gone on to other adventures in other parts of the cosmos. And for now, in this moment, in this present hour of this particular night, you are here, at rest in the most profound and relative sense, carried gently forward through the dark. There is no privileged frame of reference in the universe, no special place where true stillness can be found. And this means that your experience of rest is just as valid and just as fundamental as any other perspective. And when you close your eyes and feel the weight of your body settling into comfort, you are experiencing something real and true about your condition. Even as you simultaneously hurtle through space at velocities that would have seemed miraculous to every generation of humans that came before us. And both of these things are true at once, and neither contradicts the other. And this is one of the beautiful paradoxes of relativistic physics, that motion and rest can coexist without conflict, each true from its own perspective. And so you travel on, as you have always traveled, as every human has always traveled, as the Earth and the Moon and the Sun and the stars have always traveled, moving through the cosmos on currents of gravity and momentum that have flowed since the very beginning of time. And you need do nothing to participate in this journey. It requires nothing from you. It asks only that you rest and breathe and perhaps allow your mind to drift. And the universe will carry you gently forward through the night, through the void between the stars, through the great dark ocean of space that surrounds us all. And you will arrive, as you always arrive, at another morning, having traveled hundreds of thousands of miles through the cosmos while remaining perfectly and peacefully still.